Study all are actually discrete processes, and all the processes where Markovian, they are pure Markovian processes. Right? Now there are systems that are not pure Markovian. Actually, I never studied this sort of processes, but nowadays I found many researches that includes semi-Markov chains, semi-hidden Markov chains, hidden semi-Markov models, that means semi-assemblies. That's why let us try to understand some of the things that are not pure Markovian. We call it semi-Markovian. And what makes it semi-Markovian? That will be our topic. Mainly we will not go to the rigorous derivation of the equation, but there are rigorous derivations, and we will try to identify how can we use those, and we will actually learn the definitions, their uses. That will be our main purpose. So, the name of the chapter is Gradal theory and its application. Exactly, we will find this title in the Ross book. We will also find a chapter 6 in the textbook. And in the Ross book, you will find a chapter on renewal chapter 7. So, before going there, let us focus on this diagram. This diagram is a very interesting one. These are the processes actually that are part of Markovian systems. And you can see whenever a circle covers a number of processes, that means all the processes belong to center. Look at the heart of the process is actually PP. This stands for Gaussian process. So the Gaussian process actually is the most specialized process. The most specialized in the sense it is on the one hand a CP, that is a counting process. On the other hand, it is a Markov process. We already have seen that a Gaussian process actually is a continuous time. We already have seen. So this small circle, this one indicates Gaussian process, and when we have this one, then this says that this renewal process is a special type of counting process, and to further specialization, a renewal process becomes a Gaussian. This is clear? We started with counting process, just we defined that a counting process is something that counts the number of events, number of variables by some time t. And then actually we directly move on to the Gaussian process. Can I now tell what is the speciality of the Gaussian process as a counting process? What characteristics actually defines it as a counting process, Gaussian process? A Gaussian process actually is a counting process where interrogable times are right? Interrogable times are exponentials. And the second thing is that the Gaussian process possesses the stationary increment and the independent increment. So the very criteria here is that the interrogable times are UDP is what? It is a special type of Markov process, continuous time Markov chain, and when you further specialize a Markov process, that is there is no depth, only a path process that becomes a Gaussian. This diagram is very interesting, but not very interesting. All these processes are there. And then we have the Markov process. generalization of the Markov process is the semi-Markov process, or a specialization of the semi-Markov process is the Markov process. And finally, we have the Markov regeneration process. We do not know how far we will go, but for sure, today we will start with this one, the renewal process, and we will try to cover semi-Markov process. Time allows, if you have energy, then in the next class, we will go for Markov regeneration. Is there anyone by any chance in this class who does not have completed his or her post-graduation yet? And there is a student in this section, Mr. Elstead, right? Yes, sir. I have actually had the honor a few days back to meet, though he was actually my student in first semester and the current semester. Accidentally, I was actually in the invigilator interview to replace someone else actually who actually did the investigation on behalf of me when I was actually traveling outside. Then I went there and I found a student. I never saw him, but I found him. So anyone has any interest in me? You? So he simply vanished, right? And only surface during the exam. And not all exams, selective exams. So, any questions here? What is our motivations? Questions or motivation is not clear?
No questions.
Okay. The motivation once again is the Markov process that we have studied can be classified in different subgroups with special properties. But all the processes that we have studied before the mid-semester exams, including the queuing systems, are pure Markovian process. That is, they follow the Chapman-Kolmogorov equation and they satisfy the Markovian property. We want to actually generalize this a bit, where the process will no longer be pure Markovian. Still, some properties of the Markovian will remain, but some properties we will have that is not actually directly supporting the Markovian. So we call such a process semi-Markov process. And we will start with this one, the renewal process, and the semi-Markov process in general. Okay. The renewal process definitely is a semi-Markov process. Okay. Before starting the renewal process, one thing if we just recall or let us redefine, if we consider the discrete state stochastic processes, then actually two questions very uniquely defines the characteristics of such processes. One is, as you can recall, a discrete state process actually have states, and from one state to another state the process jumps. The jumps we call it transition. It can have a self transition in case of discrete time function. So for these processes, we have two questions, very important. Question number one actually is, where does the process go next? When the process is in state I at a certain time t, question is where the process will go next. And this actually is defined by the transition probabilities of the process. The transition probability that we already know is what? Pi is probability that if we consider from the discrete perspective, and nth step, the process always time. After one transition, the process will go to step 10. And the process will forget all the states that is being visited in the past. Hence, we say the future depends on what? Present. And that is the Markovian property. But to be satisfied this property, one more property is there that actually inherently satisfies previously. What is that? How long does the process stay in the current state? Before moving to the next state, how long the process stays in the present state? We call this one is the holding time. We define this one previously. So when we discuss the DTMC, then actually, what is the holding time?
1 by 1 minus pi.
That is the expected holding time, right? The cheat sheet has this equation. First, I received the cheat sheet of around 10 pages. Right? Most of which are very known. Most these equations actually are well known to you. Anyway, did you experience any situation where you needed some equation but that was not in the question? Actually, frequently, most of the cases equations. Right? Most of the cases you don't unless you need to know the distribution. But I think by now you know. So holding times, when we focus on discrete time, transition occurs after what? Time is divided into smaller intervals of equal length. After each interval, a transition occurs. So how long does the process actually stays in the present state? If there is no self-transition, just in the next transition we do it. And if there is self-transition, then actually the probability of such transition is the probability that the process will remain here, or 1 minus that probability is that the process will move to any of the other steps. And the number of actually interval that the process will stay here is geometrically distributed with parameter 1 minus the self-transition. Right? We know that, we discussed this. So, the holding time is what? Memory. And the distribution which is the key point is the holding time that the process stays in the current state has a distribution which is memory. And this memory property, when we define the continuous time Markov chain, we have shown that unless it is memoryless, actually the process needs to remember how long it has been in the current state and how long it will remain in the current state. So that actually violates the Markovian condition. The Markovian condition says the past cannot be considered in deciding the future of the process. That's why the DTMC is a Markov chain and it satisfies the Markovian property because the holding time is memory. When we consider the CTMC, the holding time is
exponential.
And it is also memory. Right? So these two questions collectively defines whether a stochastic process or the process is Markovian or not, and there one key property is that the holding time has to be memories. In this chapter, we will consider stochastic processes where the holding time is not memories. Rather, it has an arbitrary distribution. For example, we will consider it is biotech or any other, right? So when the holding time, the time that the process stays in the current process before moving to the next step is not exponential or geometric. It has any distribution, arbitrary distribution. Then actually we call such a process a semi-Markov process. Because why we call it semi-Markov process? This is very interesting. We call it a semi-Markov process because at some point it follows the Markovian property. Can anyone tell when does it follow the Markovian property? Say, after coming here, it stays here a binomial, a amount of time defined by binomials. Say they will move on. We have actually a very important thing here. What is that? If we just consider the transition of the process after the holding time, we ignore the holding time. Two things are there. The process is moving from one state to another, staying there for some time, then again move. If someone just consider the transitions, only the transition points, and when the process is going, then it is clear that it is still following the Markovian property. Is this clear? But when we join, the amount of time the process is going there, staying some time, then again jumping to the next step, then actually we have something that does not follow the Markovian property. But if we ignore the holding times, we just focus the transitions. When the process actually is jumping, say it is staying there, we do not actually count it. When the process just jumps, we just check whether it is jumping with the probability that is Markovian or not. If this is, then actually we call such a process an embedded Markov chain. What is embedded Markov chain? Only the transitions, ignoring the holding time, actually is a pure Markov chain. We call such a process an embedded Markov chain, and for embedded Markov chain, we can apply all the rules that we have studied in details. On the other hand, the holding times actually now does not have the numberless distribution. So, one very important thing of example is that, say, we are considering the uptime and downtime of a machine, like the IoT generator. Right? Uptime, and then it has some malfunction, some problems, and it is not working, the IoT is in doubt. And then again, some repair comes, and it is. Now, when actually this uptime and what is it? You cannot see this one? When actually the service time and the uptime are exponentially distributed, then actually by solving the continuous time Markov chain, we can calculate the fraction of time the machine is up in the long run and fraction of time the machine is down in the long run, right? By solving the steady state probabilities, the stationary probabilities. Now consider the service time and the repair time and the uptime are not exponential. But the probability from operating condition to a failure state and the probability from failure state to operating state actually is Markovian. Then how can we calculate the average runtime of the generator in the long run? Is the question clear? In case of a Markov chain, just calculate a discrete time Markov chain, Since after each time slot there is a transition, even though pi I represent what? The long run probability that there is a transition through state I. Right? And now, since time is slotted, then actually what we get? This pi I also represents the average amount of time that the process will stay in the state 1 in the long run. So if pi I is say 0.25, that means 25% of the time the process will be in state I. Why is this? Because it is memoryless and the time is slotted. In case of continuous time Markov chain, once again, since it has the memoryless distribution for the holding time, so the stationary probability also gives us the fraction of time the process will be in a particular escalation. But when we have an arbitrary distribution for the holding time, finding the long run probability of pi I or pi, pi I is for discrete time, pi I for the continuous time. For the embedded Markov chain, the embedded Markov chain has one more property. What is that? It is always discrete time Markov chain. Why so? It is not a continuous time Markov chain. Why? We know what is the embedded Markov chain, right? The Markov chain is there. The chain is there where actually the transition probabilities follow the Markovian property. But the time after which the transition occurs is not exponential, is not geometric. That means it is not memoryless. That's why what we are considering, we are ignoring the time and then just we are considering the transition points. We are actually considering the process. If this is the process, say T1, the process starts at time 0, T1 is the first transition time, T2 is the second, third. What we are doing? We are considering this point, and this point. What happens to the process? So a transition occurs here, another transition occurs here, another transition occurs there. Actually, what we are actually considering that these are one time unit. Is this clear? Then actually, then this embedded Markov chain always becomes a discrete time Markov chain. In case of a continuous time Markov chain, what happens? The holding time is exponential. But here we are considering just all the process with just after one time unit. There will be transition and the length of the time unit we do not care. We actually are oblivious to the time parameter. That's why the embedded Markov chains are discrete time Markov chain. So, if we calculate the stationary probabilities of these states, say two states, state 1 operating, working, state 2 service. Now, if we find somehow that it is half and it is half, then this says half of the times the machine will be working, half of the times the machine will be in. But the problem is, since the time that the process will be in state W or S has an arbitrary distribution, we can have that this one. Say the average for W is 10 minutes, 10 hours, and average for S is 2 hours. Then it is not the fact that half of the times the machine will be in working state, right? What is the fraction of time the machine will be in working state? Can we calculate it from now? Just it will be half into 10 divided by half into 2 plus half into 10, right? And what is the fraction?
5 by 6.
5 by 6. That means almost 84, 83 or 85% of the time the machine will be in our state. But if we just ignore the time here, then just the embedded Markov chain says the long-term probability is half that the process will be in working state, and the long-term probability is half that the process will be in services. Is this clear? So that is our objective here. Now let us see some definitions. Any question here? The only difference that we will have for this chapter is that holding time is not exponential. It can have any distribution. So what is the renewal process? Okay, let us consider you have a set of identical line paths. And unlike this two, we just use one path and that. So we start with the time starts at some point. We start with the bulb. The bulb is continuing. We do not do anything. When the bulb fades, right? Then what we do immediately? We replace it. And associated with this one, let us consider some variables. Xi. The Xi's are the lifetime of ith path. And whenever we are replacing the bulbs, when it fails, if Xi is exponential with rate lambda and Xi's are, we also assume that Xi's are IID. IID means they have the identical distribution, they are independent. When Xi's are exponentially distributed, and let's say we have a variable that counts the number of bulbs that we use by time t. Then nt is what? If you consider nt is a process, what type of process it is?
But process. But process.
Sorry?
But process. But process.
Which process?
Bath process is
Okay, it's a bar process. Right, it's a bar process. More specifically, it's a Gaussian process. It's a Gaussian process because the arrival time is exponential. Here it is not arrival. Actually, the path excess time. What we say, whenever there is a bulb which changes, then we say a renewal occurs. We renew the bulb and number of bulbs, or sometimes we say number of renewals by time t. NT represents number of renewals by time t. Then NT is a Gaussian process when Xi's are IID and exponential. As I mentioned earlier, actually we will consider holding times that are not exponential. So if Xi's are not exponential, then NT is no longer a Gaussian process. We call such a process a renewal process. Renewal process. We call such a process a renewal process because whenever the event occurs, actually we are renewing something. For example, in this case of a bulb, and bulb is running. When the bulb gets fused, what we do? We have a set of bulbs identical. We replace this one by new one. So a renewal occurs. That's why we call such a process a renewal process, and N of t represents the number of renewals up to time. This is clear. And we have one more variables, t sub n. What is that?
Renewal or exponential है
This is the time of
जैसे
nth renewal.
শু ক্লিনারের মতো একজন উঠলে আরেকজন বসে পড়ে বাট হোল্ডিং টাইমটা এক্সপোনেনশিয়াল
Time of nth renewal. Then we say such a process a renewal process, and it will be a counting process. So a renewal process becomes a counting process. Exponential with red lambda over. And a counting process actually converted to renewal process when xi is, if you go in this direction,
Anything.
arbitrary distribution. So, a generalization of the counting process is the renewal process, and this and a specialization of the renewal process is the
Counting process.
right. So the variables that we have defined here, let us put the variable actually is represented by a figure here. What is that? This x1 actually is the lifetime of the first bulb, and even one actually bulb one fused here. We've got T1 is the first renewal time. Then x2 is the lifetime of the second bulb, and why the lifetime is here? Because second event occurs here, that means second bulb gets used here. And the time, this T1 are time measured from the starting. That means from 0 to, okay? And this x is this one. So, if we concentrate on this process is a renewal process, and here we call it a counting process, but it is not a Gaussian process. The n of t actually is what? N of t is the number of renewal by time t. We already have defined. Tn is, T3 is what? T3 is the duration of time starting from the beginning up to the nth renewal. We call it, this one we call it nth renewal epoch. And finally, the x's actually are inter-event time. When this one is arbitrary, we have renewal process. When this one is exponential, we have Gaussian process. Any questions here? Any? Okay. We will compare these events here. Let's see this one and this one. First, from here, let us draw a timeline t. At this point, we have a variable t. N of t equal to n. What does this event actually represent? It represents at exactly time t, the n event occurs. In continuous sense, actually, we never say this one. But just to discuss it, for the sake of discussion, we say then a very equivalent event is are the two events identical? What's the bottom one? What's the lower one says? N event occurs, number of event occurs by time t is n. What's the first? The upper one says the nth renewal time or the nth renewal epoch is equal to, that means at time t the n event occurs. So both of these two events are identical but theoretically not usable in case of a continuous scenario. So we will not consider this one. Instead, we will consider this event. N of t is greater than or equal to n. What does it mean? by time t, n or more events. This is theoretically correct. Okay, and another one is the nth renewal epoch, Tn, is less than or equal to. My question is, are these two equivalent? Are the two events same? Who are in favor of this? That they are equivalent, and who are not in favor of this? That is, they are not equivalent. Are they equivalent? Okay, let's see. What does this one says? This one says, by time t, n or more events occur. To be that one, in the worst case, the nth event will be occurred at time t. And in the general case, somewhere here actually n occurs, n event occurs. Yes or no? Now look at the second statement. Second statement says the occurring time of the nth event, that means the nth renewal epoch, n is sub n, is less than or equal to n. Both the two statements, two events are telling the nth event occurs on or before, right? Yes or no? If both of these two events are telling that the nth event occurs on or before t, then they are identical. If they are identical, then what we can say? We can write that n of t is greater than n is equal to t sub n is less than or equal to t. Are same. More specifically, what we can write, the probability that the number of events occurs by time t is n or more is same as the probability that time to n the renewal is less than or equal to. So we agree. Similarly, we can consider that these two events are also same. So with the same argument, we can say that n is less than n and t sub n is greater than t are same. Try to figure out this one. That the nth renewal occurs on or before t. Here, the nth renewal occurs. Now, our next objective is to find the probability distribution of this one. Actually, one thing is missing here. And we need to have this one. So, let us cut it down, write it correctly. The n of t is the number of renewals up to time t is the random variable, and we have said what is the probability that it has a value is small n. This is what the probability that n sub n of t equal to what will be the distribution of this one, right? So to calculate the distribution of this one, you will find it in the book. Let's let me. I can jump it or I can write it. Okay, let us write. This probability is equal to probability that n of t is less than n plus 1 minus the probability that n of t is less than n. Is it okay? One says the probability that n less than n plus 1 event occurs. Say n equal to 5. The first one says what? By time t
6.
less than 6 equals. That means 0, 1, 2, 3, 4, 5, all are so. So by time t 0 to 5 equals. And the second one says by time t 0 to 4 event occurs. If you subtract this, then what is remaining? By time t 5 event occurs. And so this probability that n of t equals to n can be written in this way. And now what we can do? We can just apply this formula. The greater than equal to the number of renewal can be replaced by the renewal time. If we can do that, then what we can write here? Probability that t n plus 1, since here it is less than, it will be greater than t minus probability that t n is greater than t. Can I write this? Just following this one, this probability n of t greater than equal to n is same as probability t sub n is less than equal to t. So following this one, we can now, if we define one thing, that the CDF of t sub n for t is equal to what? Probability that t sub n is less than equal to, which we can write 1 minus probability that t sub n is greater than, can I write this? And this quantity we define many times as what? The complementary. Okay? We define it many times. So, this quantity can be written 1 minus probability that t sub n plus 1 is less than equal to t, minus this quantity can be written as 1 minus probability that t sub n is less than equal to t. Right? And this 1 and 1 cancel out each other, and this remains the CDF of Tn for the value t subtracted by the CDF of Tn plus 1 for the value t. So the probability that the payment that NP, the number of renewals by time t, has a value n, can be found if we know the CDF of the random variable t, right? I think there are examples in the book, or you will find it, right? Any question here? Then we will move on to the next topic. As I mentioned at the beginning of the class, most of the cases will, but there are rigorous derivations. If we find, if we search Google, if you ask ChatGPT, then ChatGPT or other generative AIs will give you many derivatives. But our objective is to understand the things, not to actually go for the rigorous derivations. What is the renewal function? The renewal function actually find out the value of, or define the value of A sub t. What is A sub t? A sub t is the expected number of renewals by, so what is n of t? by 2. Then we can say the capital X of T actually is the expected value of, right? The expected value of this one. Can we calculate this one? We can easily calculate because this one is, we know the PMF, right? We know the PMF. What happens? The text that we have actually calculated this expected value in terms of this one. They add and do it. But we will use a shortcut and we will do the same thing. What is this? This one is for all values of n, that is n equal to 0 to infinity. What we need to do? We multiply n with the BMF of, right? This is the general equation for calculating the, yes or no? What is the expected value of x? For all values of x, x is multiplied with, you will find a relation in the text that actually uses this one is then related to this one, and if you go there, what will happen? For each value of n, actually 0 will be eliminated, multiplying 0. Then you have this one, t1, then tn plus 1, then again t2, tn plus 2. So you can easily write this is nothing but does it make sense? Can I write here to here? Okay, just let me write the first term. The first term is 1 times right? What will be the second term? Second term? This one will subtract 1 from here. That's it will be a sequence of sum. Just follow the text. Or what we can do, we can actually do it in another way. This is very interesting. Actually, I understand one very new thing from here. What we can write n equal to 1 to infinity. Actually, it does not. We can replace this equation by this. The probability that n of p is greater than or equal to. Can anyone explain this? Not this part. This can be replaced by this one. If the n is non-negative and integer value. So n is first non-negative and integer value. So I am giving you this task. Next class I will ask who can explain. This equation and this next equation actually are identical. Very interesting thing is that when we move from here to here, this n is very small. Right? I want to get an answer from you. How can we actually move from here to here, subject to the fact that n will be non-negative and n will be integer? Then actually this can be written. Anyway, once we write this one, then actually it is very simple. Once again, n equal to 1 to actually infinity. This one is probability that, as we have already proved, that probability n of t is greater than equal to n is same as, what is that? T is less than equal to t of n is, t sub n is less than equal to n. So what we can write, P sub n is less than or equal to P, which actually is the CDF. So by summing the CDF, what we can calculate the expected number of renewals. That's what we call the renewal function. So if you know the CDF and you need to calculate the expected number of renewals that occurs by time, then you can easily. Any question here? Okay, if there is no question, then let us go for an example. Very simple. Let us consider a renewal process where the interval times xn, this is interval time, n equal to 1 to r IID geometry. Meaning what? We have a renewal process that is
memoryless.
That is what? Interval times geometry. That is, so what process is this one? Tell me what is the process? When the renewal process is having interval time exponential, we call it when it is geometric, it is. We started very shortly, but we did part of the process. Right? We started this one. So now, it is a bundle process. And what happens? Let's say the inter-renewal times are IID with geometric distribution, parameter P, and T1 equal to x1. Actually, we have Tn is equal to number of trials to get the nth renewal. Trials means since it is discrete time, so what we have, the time is divided into smaller unit of equal length. Let's say Tn indicates here somewhere, it indicates the number of time slots or the number of times we toss the coin or number of tries to get the nth renewal is T of P sub n. Where P1 equal to x1 represents the number of times we need to toss to get the first hit. Theory is what? If getting a hit is a renewal, then T1 is what? Number of times you need to toss to get the first hit. So if this is the case, then what we have to do, we need to find out what is the probability that N equal to K. Who can say? Is the probability? For example, you are tossing. Tail, head, tail, head, tail, two successive tail and head, right? So this Tn equal to K actually is, you can consider what is the probability that P3 equal to 7. Meaning, if you toss 7 times, then you got 3 hits. Right? Now, what is the probability? Okay, before going there, what is the distribution of N? From a Bernoulli process, the number of tries required to get nth. Who said Pascal? Who actually is supporting him? So juries are divided. One is actually Pascal, another one is
binomial.
So how many times I told the difference between binomial and Pascal? How many times? 100. So in binomial, we calculate the probability for what? What is the random variable here? What is the random here? Number of success or number of toss. So number of head or number of toss. With binomial, we count the probability of getting a certain number of heads. And in case of Pascal, we calculate the probability of getting what? We want to get some number of successes. And the randomness is what? How many times we need to try that to get that successes. That means when we are in Pascal, then actually number of tries is the random variable. Here, 10 is what? 10 indicates number of trials up to the 10th success. So it is Pascal distributed, right? And so the probability is very volunteer. Right? That's good. Very good. Now, what is the renewal process here? TN is not the renewal process, right? What is the renewal process here? What is the renewal process here that we discussed? Here, what is the renewal process?
Expected number of renewals.
N of t. T is greater than equal to Z. Why it is a renewal process? We said that a renewal process is what? A counting process. It has to count. So here, who is counting? A not sub k, k equal to A sub k is counting what? By k tries, how many heads you have got. So by k intervals, say here it is k interval, then n of k says the number of times we have got the success, number of successes that occur. So here this one is the renewal process. Is this clear? So if this is the renewal process, and we have another quantity of interest, what is that? X of n. N equal to 1, 2. What is x of n is telling you? I think I could not make it clear. You are tossing, right? We are considering a Bernoulli process. This is K. K represents what? Number of toss. Let's say the first toss produces a tail. The second one produces a tail. Then a tail, followed by head. Another tail, followed by tail. Then head, right? So the number is equation here 0, 1, 2, 3, 4, 5, 6, 7. Now, what is the value of T2? T sub 2. What does T2 represents? Number of trials
Number of heads
needed
in
to get 2 heads. What is the second head?
4.
So T sub 2 is this is clear? Okay. And now what is the what?
Four.
Okay. Just let me tell what is the value of n sub 4, n sub 5, and n sub 6. Yes or no? The number of successes up to the sixth try still remains 2. So we have got the fourth head, we got the second head, hit no head, 6 no head. So this n sub k represents or counts number of successes up to the kth try. And k value of k can be 1, 2, 3, it goes on. So we say this one is what? Process. In fact, it is the Bernoulli process. Why is it Bernoulli process? Because the xn, what is the distribution of xn? Xn is what? Number of trials we need to get a single success. So x1 represent what? Can anyone tell what is the value of x1? x2? x2?
4.
X2 is what?
4.
This xn actually is the inter-arrival time. So the x2 is the 2. x3 is 1.
3.
3, right? Now we have another variable. What is that? T1. What? Right? T2 is what? Go back here. Tn is defined as what? Number of trials to get the n. It is the minimum that we need to get the n. So T2 is what? x1
Plus x.
we have there already written here. So now the variables are
x1 की x1 inter-arrival.
xn is x3 or so on x2. Well,
Success.
now what is the distribution of xn? Okay, very good question. What is the distribution of xn?
x2 मानेंगे x2 मान 3 second the vices first headed
Sure.
quite a
You should.
can
You know it? Geometry. Because geometry is what? Repeating something until you get the success. And geometric random variable has the first system property, has the number is property, right? So, okay. এই জিনিসটা উপরে উঠে গেছে কেন আকাশে চলে গেল কেন okay anyway so the Tn probability is as we have already written n minus 1 n minus 1 into the power n 1 minus 2 k minus n right now the question is what is the probability? This probability can be calculated in many different ways. But I'm expecting the easiest one from it. And that you know, what does it say? It says that by n trials, we have by k trials, we have n
In
success.
success.
So it is very simply what? What type of random variable it is? Just these three random variables are actually related. Binomial, SQL, geometry. When the random quantity is the number of success, it is right. When the random quantity is number of trials, it is either geometric or as simple as this. How many times I told you? But this equation can be derived in very different ways. Okay. Let us forget this one. We do not go to the detail. See book. There are very different. This one is forcing us to calculate. See the book. Example 7, see the book. Before we finish, let us the renewal equation. What is that renewal equation says? The renewal equation says previously we calculated or we have shown the renewal equation, the renewal function. Where is it? Expected number of renewals, and we have given it as the sum of the sequence. Right? Now, let us redefine it in a cumulative way. Right? So, as we have already known, this one is what? The expected number of renewal by time t. Okay, before solving this one, just let me test. What is it? We did this one at the beginning of this semester as well. And your cheat sheet also include this one. So can anyone tell what is the name of this question? Some law of so the total expected value of random variable x can be calculated by considering a random variable, the conditional expectation of x condition on a value of y. This is in general an expected value is a constant. In general, an expected value is a constant, but the conditional expected value is not a constant. As y changes, the expected value changes. That's why the conditional expected value is also a random. And from here, can you recall how did we solve it? What we did in the discrete case for all values of y, we multiplied by expected values of x and y equal to y. What?
The probability.
The PMF of y. So by applying the conditional distribution of x, condition and y is equal to y, what we can do, we can calculate the total expectation of x. We do the same thing here. By conditioning on A of t, conditioning on what? The renewal time of the first renewal, T1. And then, actually, when we actually consider the T1 equal to T. That means to get the first renewal, you need a time that is T. So if this one is the case, then in general, what we can write from 0 to T. Sorry, we cannot write T here, right? Why? This T and this T are fighting, right? So what do we need to write? Just to make it simple, we write it T1 equal to 1. So from 0 to T, what happens? We consider that the first renewal occurs at time 1. Then actually we have 1 renewals plus how many renewals? Can I write this? We solve the problems of these minor, right? This is law of total expectation. What we assume that the first renewal occurs after time 1. Then we are calculating the expected number of renewals. So we are now sure with this assumption that the first renewal occurs by time 1. So that's why we add 1. And the remaining T minus Y time, now we will calculate the number of expected number of renewals. And since we consider this, we multiply with this PDF. Right? And if we solve it, then this one multiplied with just 1 or 2 minutes. This one will give you the CDF of T for the value T, plus from 0 to T, expected number of renewals will be given this one multiplied with FTY dy. So this equation actually is a linear equation, and we call this equation linear function. Using this one, we can calculate different for different problems expected number of renewals. We'll see in the next class, or we'll move on to the 7 out of 10. S2. I have, you have a class in this way. The problem is there is a conference or something like this from Bangladesh government in the next week. 26